There is a well-established relation between the size of the open velar port and the position of the velum. In addition, though, to varying with port area, velar position also varies when the port is completely closed. These adjustments result from the anatomical relationship between the velum and the levator palatini muscle. Since the muscle's superior attachment lies well above the level at which port closure is complete, increasing contraction of this muscle continues to raise the velum even after closure has occurred. As a result, changes in the vertical position of the velum throughout its range of movement are presumed to reflect general velar control strategies, and our study of them is not limited to pieces of speech having an open port. Being able to monitor the vertical position of the velum throughout its range should aid in the discovery of the principles of normal velar motor control, as well as increasing our ability to evaluate velar control problems in some clinical populations. The velotrace was developed to allow us to monitor these changes in velar position. It allows us to collect mid-sagittal velar position data in analog form, eliminating X-ray exposure to the subject, and frame-by-frame measurements of cine and video recordings by the investigator.
It's a long sol again. It's a long sol again.
In this drawing of the velotrace, we see its three major parts: an internal lever, an external lever, and a push rod between them, all carried on a thin support rod. The levers are connected to the push rod so that when the internal lever is raised, the external lever is deflected toward the subject. The device is loaded with a small spring to improve its frequency response, and thus the ability of the internal lever to follow rapid downward movements of the velum. Movements of the external lever can be monitored in several different ways. For example, one might use a velocity displacement transducer that would make the velotrace a convenient standalone device for the clinical evaluation of velar movement. This diagram shows another approach: optoelectronic tracking. In the system we've been using, a light-emitting diode, or LED, is attached to the end of the external lever to allow us to monitor the movement of the lever about its fulcrum. A second LED is positioned at the end of the support rod, and a third near the bridge of the nose. These serve as reference points against which the movements of the external lever can be described, including making corrections for head movement. The positions of the LEDs are tracked in two-dimensional space and recorded simultaneously with the acoustic signal and a timing signal on a multi-channel instrumentation data recorder. Before inserting the velotrace, topical anesthetic and decongestants are applied to the nasal mucosa. The velotrace is then inserted using a procedure similar to that used for nasal catheterization. And although it's a rigid device, the insertion is easy unless the subject has serious nasal pathologies or deformities. Finally, an external clamp attached to a headband is used to stabilize the position of the velotrace over the course of the recording session. Here we see the relative size and positioning of the velotrace in a life-size model. Several studies were done to evaluate the velotrace. In one study, we examined the ability of the velotrace to follow rapid downward and upward movements of the velum. Velotrace data were compared with data obtained through frame-by-frame measurements of cine films photographed through a nasally positioned fiber optic endoscope, and some of those data are shown in this figure. Velar position time functions are shown for two different test words: FEESMEEP in the left panels and FEMZEEP in the right panels. Data were recorded with an endoscope for one subject, the upper panels, and with the velotrace for another subject. In all cases, the traces represent ensemble averages of a set of tokens of the same utterance type. Clearly, the patterns are similar for the ensemble averaged velotrace data and the ensemble averaged frame-by-frame endoscope data, despite the fact that the data were obtained from two different speakers. In a second evaluation study, cineradiographic films and velotrace data were obtained simultaneously from a single subject. The velotrace was positioned in one of the subject's nasal cavities, and a thin gold chain was inserted through the other nasal cavity and positioned along the velum and down into the oropharynx. The frame-by-frame measurements made of the highest point of the velum and of the vertical position of the tip of the internal lever are seen in this figure. The very high linear correlation between these measures is reflected in this scatter plot and the correlation coefficient of 0.993. In addition, velocity measures obtained from our velotrace data were consistent with velar velocity data reported in the literature. It appears that movements of the velotrace reflect the movements of the velum itself. Here is a subject producing repetitions of phrases used in a recent study.
It's a long sol again. It's a long sol again. It's a long sol again. It's say la 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 sol again.
These traces represent movements of the external lever for the utterance we just heard. It's say la sol again. The velum moves up for the TS of its. Then down a bit for A, L, and A. Then up again for S and then G, and down for the N of again. Now let's look at some data. This figure shows velocity traces, movement patterns, and acoustic waveforms for three utterances. It's lon sol again, it's a lon sol again, and it's say lon sol again. The data were corrected for head movement, and the signal was smoothed. We marked the beginning of the nasal consonant N in the acoustic waveform, and also the beginning of each velum lowering movement between the S of its and the N of lon sol, using the velocity trace to determine the beginning of each movement. In each case, the large lowering movement for N is highlighted in yellow. In the longer sequences, we also found an early shallow movement that we've highlighted in purple.
This figure shows how revealing comparisons between oral and nasal sequences can be. These are movement traces for sequences with and without a nasal consonant. In the top panel, you see the sequences it's a la sol again and it's a lon sol again, superimposed on each other. Notice that the velum moves from its high position for the S of its into a lower position in both kinds of sequence. However, in the oral sequence, the velum then rises for the S of la sol, whereas in the nasal sequence, it continues lowering for the nasal consonant of lon sol. This figure shows that the early shallow movement in the nasal string is related to the string a la, while the later, more extreme movement is associated with the nasal consonant. The lower figure shows the corresponding data for it's say la sol again and it's say lon sol again. Here we see again that the oral sequence contains lowering movements that are mirrored in the nasal sequence, and that the lowering for the nasal consonant itself occurs relatively late. We used these data to help us understand the interaction between intrinsic segmental requirements of the velum and extent of velar coarticulation for a nasal consonant. Here we presented them to show you how this device works, what kind of data can be obtained, and how those data can be analyzed. Obtaining the acoustic signal simultaneously with the velotrace signal made it possible to identify the acoustic segments, and processing the velotrace signal to obtain the instantaneous velocity made it possible to identify the beginning and end of each movement. Although we did not obtain movement data for other articulators in this study, we have, in other studies, collected lip and jaw movement data along with the velotrace data. In those, we examined interarticulator coordination in the production of nasal consonants. We have found that velotrace data are relatively easy to obtain and allow us to use efficient analysis procedures while avoiding the risk of X-ray exposure for the subject.
The details of tongue movements during speech are of great interest to anyone involved in understanding the processes of speech communication, particularly phoneticians and speech and language pathologists. With electropalatography, or EPG for short, it's possible to record one important aspect of tongue activity: the location and timing of tongue contacts with the hard palate during connected speech. First, we construct a thin acrylic palate made from a plaster impression. It has 62 silver electrodes serving as contact points embedded in the material. The rows of electrodes are placed according to anatomical landmarks. For example, the back row is at the junction between the hard and soft palates, and the front row at the place where the upper front teeth meet the alveolar ridge. Rows are placed proportionately on the surface, with the front 4 rows being closer together than the back 4 rows. Wires from each electrode are fed into 2 cables which pass out of the subject's mouth at the corners, usually behind the wisdom teeth, so as to interfere as little as possible with normal speech. Once the subject has the palate in place, she plugs into a multiplexer unit worn around her neck and connects to the computer interface. A circuit is completed by means of a handheld electrode, and contact patterns are now displayed on the computer screen. The points on the screen represent the electrode positions, with the alveolar region at the top. Contact is shown by filled white squares. Note that the computer display shows a symmetrical arrangement of the electrodes. In actual fact, the front 4 rows, as seen earlier, are concentrated in the anterior parts of the palate. The rows of electrodes can be related to the place of articulation labels commonly used in phonetics. We will now demonstrate the contact patterns of some English sounds. EPG is particularly useful for showing place of articulation for alveolar and velar plosives. First, alveolar plosives.
Ta. Ta.
During the closure phase of the plosive, note the full contact at the alveolar ridge and along both sides. Next, velar plosives.
Ka. Ka.
Full closure is now at the velar region. Co-articulatory effects can be shown very clearly with EPG. Compare, for example,
Ka. Ke. Ka. Ke. Ka. Ke.
Note the greater amount of contact for the plosive in A key, reflecting the higher and more forward placement of the tongue in anticipation of the E vowel. Different manners of articulation can also be illustrated with EPG. Alveolar and post-alveolar fricatives show characteristic patterns of contact. First, alveolar fricatives.
Asa. Asa.
A narrow central groove can be seen clearly along with full lateral contact. Next, post-alveolar fricatives.
Asha. Asha.
As with the alveolar fricative, a groove is present, but it's wider and in a more retracted position. Lateral approximants also show distinctive patterns of contact which depend greatly on the vowel environment. Compare, for example,
Allah. Allah.
and
Ali. Ali.
the dynamics of tongue activity in more exotic sounds can be studied with EPG. For example,
Ara. Ara.
a A slow-motion replay reveals the individual alveolar contacts during production of the trill. Sounds produced with a velaric airstream mechanism, such as clicks, reveal interesting information about tongue dynamics. An alveolar click shows near simultaneous alveolar and velar contact.
The technique can thus provide very revealing information on the dynamics of tongue activity for specific sounds. With the computer, it's possible to examine what happens to these sounds in connected speech. I've recorded a sentence here, and we can analyse the EPG signal along with the acoustic waveform. First, let's hear the sentence.
Take another cocktail.
As I move the cursor through the sentence, we can see changing patterns of EPG contact. I'm placing the cursor here at the end of the word TED. Where you would expect a D with alveolar contact. Note, however, that the D is completely assimilated into the place of articulation of the following velar closure. Moving further into the utterance, at the end of the first vowel in the word cocktail, note first the velar closure, then the alveolar, with a brief period of simultaneous or double articulation. This display shows a sequence of palatal frames sampled at 10 millisecond intervals for the initial plosive in the word TED. From this full contact data, a graph can be constructed showing the total number of contacts occurring in different regions of the palate. Here we see a display showing the total number of contacts in 3 regions of the palate for the first 100 frames in the utterance. Another data reduction facility is a centre of gravity plot. Centre of gravity shows a concentration of contacts in different parts of the palate. Here the centre of gravity is plotted as a function of the total number of electrodes. The graph shows movement in the centre of gravity from the front of the palate to the right of the graph to the back in the word TED, spoken here with the assimilated final plosive. This plot shows the frequency of contact of each electrode over a specified portion of the utterance. EPG is thus very suited for studying the sorts of connected speech processes that occur when we speak normally and spontaneously.
EPG is proving to be a valuable clinical tool for assessing and treating a wide range of speech disorders. The technique can provide details of tongue movements that aren't always obvious from an auditory analysis. Peter was aged 9.5 years when he was referred for EPG therapy. He was born with a unilateral cleft lip and palate. This was repaired surgically before he was a year old. Despite early surgery, his speech problems persisted through the preschool years, and this might have been hindered by conductive hearing loss. Recent video fluoroscopy had shown his velopharyngeal competence to be normal.
Production of the grooved sibilant S was obviously distorted, with nasal escape of air. The EPG patterns during target S show complete constriction in the velar region. Interestingly, this feature of complete contact in the velar region occurred not just for S, but for all anterior obstruents. The cursor is now placed during the bilabial stop in the word biscuit. In a normal speaker, there would be minimal tongue-palate contact here,
but Peter shows evidence of complete velar closure. The cursor is now placed during the final alveolar closure in the word biscuit. Note the abnormal double alveolar velar articulation. These double articulations were not obvious from the auditory analysis. Subsequent therapy for Peter involved inhibiting these abnormal double articulations, as well as trying to establish a more normal-looking alveolar groove configuration for S. The type of visual feedback provided by EPG helps children to understand exactly which articulatory gestures they're producing incorrectly. It also gives them immediate feedback when they try to monitor or change their own articulatory patterns. In a recent project funded by the British Medical Research Council, we used EPG to record and treat 20 school-aged children with articulation disorders which had proved to be resistant to conventional therapy. The results so far have proved very positive. Here are some examples of EPG patterns before and after therapy. These EPG patterns are from 5 children who took part in the project. The target sound is the S in a castle. One frame only has been selected, that of maximum constriction during S production. The 5 children had a variety of abnormal patterns for S before therapy. After therapy with EPG, the patterns more closely resembled a normal S configuration, and they were also heard as acceptable productions. In the future, we need to continue to construct and carry out clinical trials using EPG so that clinicians can begin to recognize which client groups can benefit from this new approach to therapy. So EPG offers exciting new prospects both as a laboratory and a clinical technique.
Since speech production is very variable, large quantities of kinematic data are needed to help uncover underlying principles of speech motor control. Therefore, we should have efficient techniques to gather and analyze articulatory data.
Electromagnetic mid-sagittal articulometer systems, which we call EMMA systems, make it possible to record movements of multiple midline points on vocal tract structures. Although these systems can be expensive, they are within reach of individual laboratories. If used correctly, they can provide the needed quantities of accurate articulatory data with minimal risk to experimental subjects. In the EMMA system that we developed and use at MIT, 3 transmitter coils are held in a transmitter assembly, with the coil axes perpendicular to the midline plane. The transmitter assembly is positioned on a subject so its midline coincides with the mid-sagittal plane. Each transmitter is excited by a sinusoidal signal at a different frequency, between 60 and 80 kilohertz, generating an alternating magnetic field with a strength that decreases in proportion to the cube of the distance from the transmitter. Small, encased transducer coils are mounted on the subject's articulators. They can be mounted on the tongue blade, tongue body, lower incisors, lips, and possibly the velum. Transducers are also mounted on the bridge of the nose and upper central incisors for a maxillary frame of reference. In order to obtain accurate data, the transducers are mounted as close as possible to the midline, with their axes parallel to the transmitter axes. The alternating magnetic fields from the transmitters induce alternating voltages in the transducers, which are connected to receiver electronics with fine insulated wires. The electronics convert the induced high-frequency signals to 3 slowly varying output signals from each transducer. These signals are digitized along with the speech signal. We can also digitize simultaneously the output of other transducers. The digitized signals are converted by signal processing software to X and Y coordinates in the midline plane. As the articulators move, the transducer axes can vary in their alignment with the transmitter axes, causing potential measurement error. The signal processing software includes a calculation that corrects for this rotational misalignment. The field strengths and frequencies delivered to a subject by our EMMA system are similar to the ones experienced by the user of an engineering workstation. Generally, it's thought that such fields are not harmful to non-pregnant adults. But since there are unanswered questions about this issue, we pay careful attention to new studies of the effects of magnetic fields like these on humans. Before each experimental run, we perform 2 types of calibrations, both of which are needed by the signal processing to produce accurate measurements. We calibrate the fields to obtain exponents that characterize how the field strengths change with distance from the transmitters. Data are generated for the field calibrations by moving a transducer through several circles of known radius. The transducers are calibrated to obtain individual gain and offset scale factors. We gather data for each transducer calibration by placing it in a number of known locations in the midline plane. The subject is seated in a comfortable position, and the transmitter assembly is placed over and secured to his head. The assembly is positioned vertically and horizontally, so the center of the measurement plane coincides with the subject's oral cavity. We check and adjust the alignment of the assembly midline with the subject's mid-sagittal plane, using the midline pointer being manipulated by the experimenter. Then we put midline marks on the subject's face as a guide to transducer placement. Next, we mount the transducers on the subject's articulators. We use a biocompatible rubber cement for extraoral placements and a biocompatible cyanoacrylate for intraoral placements. As we mount each transducer, we position it as close as possible to the midline, and we keep its axis perpendicular to the mid-sagittal plane. In addition to accurate calibrations, the integrity of the data depends very much on the careful placement of transducers on the subject. We check each placement to be sure that no transducer is more than 3 millimeters from the midline, because the misalignment correction algorithm is increasingly less effective with transducer placements that are further from the midline. This time, in attempting to provide a clear view for the video camera, we placed some transducers unusually far to the subject's right, very near the tolerable limit. Normally, we would reposition these transducers. We can record about an hour's worth of data. The recording time is usually limited by how long the intraoral transducers remain mounted securely. While the subject reads the text, an experimenter checks to be sure that the transducers remain in place and that the subject continues to be aligned in the transmitter assembly.
They read who'd had it, they read who'd hit it, they read who'd had it, they read who'd hit it, they read who'd hit it, they read who'd had it.
At the same time, the transduced positions are monitored on a real-time display to check for changes that might indicate loosening of an attachment or excessive misalignment.
They read who'd hit it, they read who'd hit it.
We also make a video recording of the subject's lips. This recording is synchronized with the EMMA recording, so we can relate EMMA data on lip positions to labial cross-sectional areas. When the speech data have been collected, we record the shape of the subject's palate by drawing a transducer along its midline. In addition, we record the orientation of the occlusal plane by having the subject bite lightly on a plate that has 2 transducers mounted on it. The more anterior transducer is positioned just forward of the upper incisors. When the experiment is over, the transducers are removed carefully from the subject and the transmitter assembly is lifted off. Next, we run a program that performs the signal processing. For each transducer, the resulting signals consist of X and Y components of displacement, velocity, and acceleration versus time, as well as time-varying magnitudes of velocity and acceleration, and a measure of the amount of misalignment correction called the correction index. The transducer coordinates are calculated with respect to the fixed maxillary transducer locations, and they are translated and rotated to the occlusal plane frame of reference. We examine the results with a program that allows us to listen to the speech and label events on the waveforms. In this display, the top window shows the RMS of the speech signal for 5 utterances. We can listen to the signal to locate the desired utterance.
Ma, who hit it? Ma, who had it? Ma, who hit it? Ma, who hit it? Ma, who had it?
Now we delimit the utterance we are interested in with 2 cursors, which causes the delimited speech signal and a selected set of articulatory signals to be displayed below on the left. For orientation purposes, Y versus X trajectories are shown for transducers on the tongue body, lower incisor, lower lip, and upper lip, along with an outline of the hard palate. The articulatory signals at the left are the values of the misalignment correction index versus time for the 4 transducers. As is typical, the tongue transducer shows the largest amount of index variability. We check the correction index for abnormally large values, and we listen to the pronunciation of the utterance. If these are acceptable, we enter a phonetic label to identify the utterance. If not, we bypass the token. Here, the signals on the lower left are for the tongue body X and Y coordinates and the absolute value of tongue body velocity versus time for the utterance, Ma, who hit it? At the lower right is an expanded plot of tongue body Y versus X. The spacing between the points corresponds to the 3.2 millisecond sampling period. The scale bars show 1 millimeter. The 2 channel numbers mark the beginning of the trajectory. As we place the cursor on the time signals, a crosshair is displayed on the trajectory at the selected time. Here we can see the locations on the trajectory that correspond to the time of the beginning of the ah, the end of the ah, the beginning of the oo, and the end of the oo. At the time near the middle of the oo, there is a velocity minimum, which corresponds to the extreme extent of tongue body movement towards the oo target. For subsequent analysis, we label the beginning and end of the oo with the help of the display of the expanded acoustic signal shown above the trajectory plot. Next, the labeled acoustic events are used to guide algorithmic data extraction. The signals on the lower left are velocity magnitude versus time for the 4 transducers. On the lower right are expanded XY trajectories. First, mid-val spectra of the acoustic signal are displayed with algorithmically picked LPC peaks. Then, the cursor and crosshairs move automatically to the time of the minimum velocity for each transducer, for extraction of X and Y coordinates. At each step, the experimenter checks the operation of the algorithm. With experimenter approval or correction if necessary, formant values, transducer coordinates, minimum velocity times, and correction index values are written to a text file for subsequent graphical and statistical analysis. This system is flexible, so it can be programmed readily to perform a wide variety of data extraction algorithms. It can also be helpful to examine articulatory trajectories for multiple repetitions of an utterance, to investigate directions of movement, trajectory shapes, and token-to-token variability. In this example, we see a Y versus X trajectory for the tongue body in pronunciation of the utterance he ga. The numbers on the trajectories indicate labeled times of acoustic events. They correspond to the onset of the E, onset of the G, release of the G, onset of the ah, and end of the ah. The G is produced with a forward tongue body movement, which, because of the context, results in a looping trajectory. Examination of a sequence of such plots for multiple utterances shows some variation, but a rather consistent looping trajectory for the G. It can also be helpful to show a number of such trajectories on a single display for comparison purposes. With these systems, there is no way to determine absolutely how large the measurement error might be, so it's important to explore the data for indications of possible measurement error. To do so, we examine time series plots of extracted data. Each column of points in this plot represents correction index values from several transducers for one token. The horizontal axis shows time in seconds. Here we see an increase in variability of values of the tongue body correction index that was associated with loosening of the transducer toward the end of the run. Tongue body data from this point on are suspect, so they are discarded. This figure shows an example of EMMA data. The symbols indicate locations of transducers on the upper and lower lips, the tongue blade, the tongue body, and the lower incisors for multiple repetitions of the vowel oo spoken in a carrier phrase. The panel on the right shows data collected while a subject was holding a 1 centimeter bite block between the molar teeth on one side during the second half of the experiment. In the bite block condition, the lips and tongue are raised with respect to the mandible to compensate for its lowered position. This plot shows the same tongue body data from before the bite block and with the bite block. During the bite block condition, there is increased token-to-token variability of tongue positions in the direction normal to the vocal tract midline. EMMA systems can provide large quantities of accurate data on the movements of mid-sagittal points on vocal tract structures. Since there are potential sources of measurement error which can't be controlled for in an absolute sense, it's important to calibrate and use such systems very carefully in order to assure accuracy of the data. The challenge is then shifted from data collection to designing useful experiments and analyzing results in the most productive and insightful way.
I understand this. Like I said, it'll sit for a long time. Yeah. Are you busy these days? Or? Yes, very busy.
Speech production involves the coordinated activity of many anatomical structures, including the lungs, larynx, tongue, jaw, and lips. Of these, only the jaw and lips can be observed fairly easily and non-invasively, because their activity is externally visible. This video presents several experimental applications for examining these structures using OptiTrack, a state-of-the-art optical tracking system that accurately measures three-dimensional position of infrared light-emitting diodes attached to the structures of interest.
And then
The primary component of the OptiTrack system is the camera bar, which may be mounted vertically or horizontally, as shown here. The bar contains 3 fixed focus lenses, and each lens consists of a single-axis element that detects more than 2,000 positions along its axis of orientation. Onboard algorithms increase the accuracy of the system to at least a few hundredths of a millimeter, depending on experimental conditions and the type of motion. Three-dimensional marker positions are calculated from the known position and orientation of the 3 lenses. Total sampling rate of the system is about 3,500 hertz. Typically, we use 10 to 20 markers whose 3D positions are measured between 100 and 250 times per second. The camera is calibrated automatically when the system is turned on, resulting in a 1-meter viewing cube at a camera-to-subject distance of about 2 meters.
This large viewing area means that subjects do not have to remain perfectly still. On the other hand, rather large markers must be used to generate a consistently detectable light source. First, we show a simple setup in which small markers are placed mid-sagittally on the lips and larger markers on either side of the chin.
Babi boo bebo, 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 babi boo bebo.
Until recently, most optical tracking studies of the lips and jaw were set up this way and were further restricted to measuring only 1 or 2 dimensions of motion. Clearly, this configuration captures only a fraction of the lip behavior, particularly during vowel rounding. Yet, comparing articulatory events, such as the peaks and valleys in the position time series corresponding to bilabial closures and different vowels, has provided much valuable information about articulator timing and coordination during normal and disordered productions. Since the OptiTrack measures 3D position of as many markers as we like, we can put them wherever we want, as shown in this next setup, which we are using to examine facial contour and motion during speech. Data acquisition is controlled from the PC, which stores the marker data in a separate file for each trial.
Good. Okay, next trial, ba-ba-ba-ba. Ready? Go. Ba-ba-ba-ba, ba-ba-ba-ba, ba-ba-ba-ba.
Marker positions can be viewed in real time, or the files can be played back from within the data collection program. For these data, stick figures are used to connect the 8 lip markers and the 10 markers on the forehead, nose, cheeks, and chin.
Okay, we're going to practice now doing the Japanese vowels. Can you start now? Babi-boo bebo.
Adding a profile view gives the display depth and enables all 3 dimensions to be seen simultaneously. Note the substantial protrusion of the entire lip structure and cheek during production of the rounded vowels. In addition to marker position data, optional multi-channel AD converters can be used to record other analog and digital signals, such as muscle EMG, electropalatography, and of course the speech acoustics. The next demonstration shows a cheerful subject with surface electrodes already in place for transducing EMG activity of various orofacial muscles. A rigid head mount is used to remove the distorting effects of head motion on the lip and jaw data. Instead of placing markers on the chin, whose soft tissue may move independently of the jaw, a rigid splint is fitted to the lower teeth.
Pop, 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 pop. Pop, pop, pop. It's good. Fa, 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 fa. Pop, 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 pop. Ba, 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 ba.
We have used muscle signals like these to model the dynamics governing lip and jaw motion during repetitive speech sequences such as the following.
Ba, 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 ba. Ba, 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 ba. Ba, 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 ba. Ba, 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 ba.
The frontal view of the lip markers and the jaw bar is shown on the left. The very uniform time series for vertical positions are shown on the right. Real speech is not nearly so tidy.
Pam put the bobbin in the frying pan. Mommy added more pumpkin parts to the boiling potato soup. Pam put the bobbin in the frying pan.
The greater diversity of these data points up an important limitation of optical tracking techniques and the need for caution in interpreting different utterance types. Throughout the repetitive speech sequence, shown again at slower speed, the jaw and lips are the primary articulators, and their behavior is rhythmic and highly coupled, as seen in the nearly identical lower lip and jaw traces. However, because of the phonetic diversity of the more natural utterance, the lips and jaw are not always primary articulators, and each interacts differently with the tongue, whose motion is inaccessible to us. With these differences in mind, we proceed to the analysis of the muscle EMG, movement, and acoustic signals. Basic signal conditioning, such as filtering, and various manipulations of the movement data may be done using optional OptiTrack software. Data measurement and analysis, however, must be done elsewhere. The final experimental demonstration shows the system's ability to make complex coordinate transformations needed for rigid body analysis of the individual components of the jaw's 3D motion. Markers are attached to sturdy lightweight frames that span relatively large distances and which move in unison with the head and jaw. The system must compute 2 coordinate transformations in order to specify jaw motion in its own frame of reference. Starting at the lower left of the figure, the first transform is from the world view of the optotract to that of the head. This transform is necessary for basic head movement correction. The second transform puts the jaw into its own coordinate system, which remains fixed regardless of its motion relative to the head. The origin is determined by the experimenter. For the study exemplified here, the intersection of the three axes is midway between the two jaw condyles, with the horizontal axis parallel to the jaw's occlusal bite plane. The transformed jaw motion is fully specified by rotation of the three orientation angles and translation of the three positions.
Okay, how does that feel? Can you move around a little bit? Okay, why don't you try the trial? How much you get? Okay, why don't you start?
Asasa, 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 asasa.
Although humans can move their jaws through all 6 degrees of freedom, for example during chewing, we have observed only 3 principal components of jaw motion during nonsense productions, all of which fall within the mid-sagittal plane. Shown on the right, these are horizontal and vertical translation and sagittal rotation of the jaw condyle.
Akaka, 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 akaka.
Compared to the Asasa productions, production of K entails quite different initial orientation angles, as well as differences in the relative amounts of horizontal and vertical translation. In summary, pre-calibration of the camera and the data acquisition software included with the system make it easy to use. The system has high spatial accuracy in 3 dimensions and adequate sampling speed for measuring a wide range of behaviors associated with speech. Simultaneous multiple-channel analog and digital recording is possible using optional components. The ability to track many markers and calculate coordinate transforms makes head movement correction possible, as well as complex rigid body reconstructions. These features are particularly useful in situations where subject mobility is not easily controlled. The following is a list of specifications that reflects our experience with our own OptiTrack systems. Newer systems may have different levels of performance.